Imagine a world so colossal it blots out its own sun, a planet so huge it turns day into an unnerving premature night, one transit, one colossal shadow sweeping across a hypothetical moon, and an unsettling question that echoes through the cosmos: how big can a planet really get before it stops being a planet at all? The universe is filled with giants that dwarf our own, worlds that exist on a scale so vast it borders on the incomprehensible. These are not just bigger versions of Jupiter. They are fundamentally different kinds of celestial bodies, governed by extreme physics that challenge our very definition of what a planet is. They are beautiful, they are mysterious, and as we'll discover, they are utterly terrifying. Before we crown a champion, we need to define the terms of the competition. What does biggest truly mean? It's a question with two very different answers. First, there's biggest by radius, how much space a planet occupies, how swollen and visually imposing it is. These are the cosmic balloons, planets that have puffed up to enormous sizes, often due to intense heat from their parent stars. Their atmospheres are vast, but incredibly tenuous. Then, there's biggest by mass, how much stuff a planet is actually made of, the sheer quantity of matter packed into its core and envelope. These are the cosmic anvils. They might not always look as large as their puffy cousins, but their gravitational pull is immense, crushing everything with unimaginable force. A planet can be large in volume but light in substance, or it can be compact yet unbelievably dense. This fundamental difference splits the contenders for the title of biggest into two distinct categories of giants. To understand the extremes, we must first establish a baseline. Let's start at home, with the undisputed king of our own solar system, Jupiter. This is a world so large, you could fit all the other planets in our solar system inside it, with room to spare. Over 1,000 Earths could be poured into its volume like marbles into a jar. Its great red spot is a storm that has raged for centuries, a hurricane wider than our entire planet. Its lightning flashes are hundreds of times more powerful than anything on Earth, capable of blinding a camera from orbit. Jupiter's immense gravity acts as a cosmic bouncer, flinging asteroids and comets out of the inner solar system. Even here, in our familiar celestial neighborhood, we see that giants are not gentle. They are powerful, chaotic, and profoundly dangerous. Now take this blueprint and imagine what happens when you turn every dial up to 11. Let's explore our first category, the biggest planets by radius. To create these behemoths, the universe follows a simple recipe. Take a gas giant like Jupiter and push it dangerously close to its star. We call these worlds hot Jupiters, bathed in radiation thousands of times more intense than what Earth receives. Their atmospheres boil and swell. The day side, permanently facing the star, can reach temperatures hot enough to melt iron, causing it to glow with a dull, menacing red. This intense heat inflates the planet's gaseous envelope like a hot air balloon, expanding its radius to truly colossal proportions. The outer layers of the atmosphere are literally blasted away into space, forming a magnificent comet-like tail that trails the planet for millions of kilometers. So, who are the champions of size? Meet the puffy planets, worlds like WASP-17b or HATP-67b. These are some of the largest planets ever discovered by radius, measuring nearly twice the diameter of Jupiter. Yet, they are deceptively lightweight, containing only about half of Jupiter's mass. This makes their average density incredibly low, so low in fact, that it's comparable to styrofoam or balsa wood. If you could find a bathtub large enough, these planets would float. Their atmospheres are so vast and diffuse that they appear translucent, a ghostly, glowing sphere hanging in space. They are enormous to the eye, but fundamentally airy and fragile, stretched to their absolute limits by the relentless energy of their star. They are the undisputed kings of volume. The weather on these worlds is not weather as we know it, it's a physical nightmare. Supersonic jet streams, driven by the extreme temperature difference between the blistering day side and the frigid night side, scream around the planet at thousands of kilometers per hour, circling the entire globe in a matter of hours. On the night side, away from the star's direct glare, conditions are just right for clouds of vaporized rock and iron to condense. It likely rains liquid iron, glass, and molten minerals. These storms rage with unimaginable ferocity, with lightning arcing between cloud decks that float above an abyss. There's no ground to stand on, no surface to ever reach, only an endless turbulent atmosphere that grows hotter and denser the deeper you fall. Now for our second category, biggest by mass. Here we enter the realm of the super Jupiters. These are the true heavyweights of the cosmos. As you pile more and more mass onto a gas giant, something interesting happens. Beyond a certain point, adding more mass doesn't make the planet bigger by radius. Instead, the immense gravity begins to compress the planet, making it denser and denser. These worlds can have 5, 10, or even 12 times the mass of Jupiter, but remain roughly the same size. They are cosmic cannonballs. As they approach a truly critical threshold, the lines begin to blur. Around 13 times the mass of Jupiter, the pressure and temperature at the planet's core become so extreme that a new process can ignite: the fusion of deuterium, a heavy isotope of hydrogen. This is the official, albeit debated, dividing line between a giant planet and a brown dwarf, or a failed star. At this point, the object begins to generate its own faint light and heat. The taxonomy gets tricky, and we're left questioning if we're looking at a planet at all, or the smallest possible ember of a star that never was. And then there are the accessories. Size isn't just about the planet itself, but what surrounds it. Astronomers have found a candidate, a young object named J1407b that has been dubbed a super Saturn. Its ring system is so vast, so utterly gargantuan, that it makes Saturn's rings look like a tiny, faint wisp. Spanning nearly 180 million kilometers from end to end, wider than the distance between the Earth and the Sun, this system contains an amount of material equivalent to the mass of our entire planet. If this object were to replace Saturn in our own solar system, its rings would dominate our night sky, appearing many times larger than the full moon. For any moons orbiting within this system, the rings would turn the sky into a set of cosmic Venetian blinds, with the stars' light flickering on and off as the dense bands of dust and ice pass by, creating eclipses that could last for months at a time. While the exact nature of J1407b is still debated, it could be a massive planet or a small brown dwarf. Its rings represent a scale of structure we once thought impossible. So why is all of this so terrifying? The single biggest reason is gravity. Giant planets are not just objects, they are deep, steep wells in the fabric of space-time. The more massive the planet, the deeper the well. To leave Earth, a rocket needs to reach an escape velocity of about 11 kilometers per second. To escape Jupiter, that number jumps to nearly 60. For a super Jupiter, it could be hundreds. A spacecraft that ventures too close, dipping below a critical altitude, would find itself in a gravitational prison. No amount of conventional fuel would be enough to climb back out. The ship would be doomed to an endless, accelerating fall, pulled down into the planet's crushing depths. It's a one-way trip from which there is no return. And what a fall it would be. There's no solid surface to crash on, only an endless plunge into an atmosphere that becomes progressively more hostile. As a probe descends, the pressure would rise relentlessly, from 1 bar to 100 to 1,000 to millions of times the pressure at sea level on Earth. The hull of any conceivable spacecraft would groan, buckle, and then implode into a ball of scrap metal. Simultaneously, the temperature would soar. The probe would be cooked, its materials first liquefying, then vaporizing, and finally, at depths we can barely imagine, the very atoms would be torn apart by the heat and pressure. The probe wouldn't just be destroyed, it would be unmade, its constituent particles dissolving into the swirling metallic hydrogen sea of the planet's dark, violent interior. Even if you could somehow survive the gravity and the descent, there's another invisible killer: radiation. Massive planets generate immensely powerful magnetic fields, creating magnetospheres that dwarf our own. These fields trap high-energy particles from their star and from deep space, funneling them into intense radiation belts, far more lethal than Earth's Van Allen belts. Auroras, instead of being gentle curtains of light, would be roaring, planet-spanning storms of energy, visible across the electromagnetic spectrum. For any spacecraft, or any hypothetical life, this environment is a death sentence. A constant storm of particles would bombard the ship, frying electronics, corrupting data, and delivering a fatal dose of radiation in mere seconds. Even the most advanced shielding would groan under the assault, slowly failing as the planet's magnetic fury tears it apart. With all these known giants, a chilling thought emerges. Could there be even bigger ones out there? The answer is almost certainly yes. Our methods for finding exoplanets have a built-in selection bias. The most common method, the transit method used by telescopes like Kepler and TSS, is best at finding large planets that orbit their stars very closely and quickly. It relies on seeing the dip in starlight as a planet passes in front. This means we are excellent at finding hot Jupiters. But a truly massive giant on a long, distant orbit, a cold Jupiter hundreds of times further out, taking centuries to complete one orbit, would be nearly invisible to us. We would have to stare at its star for generations to catch a single transit. The cosmos is wide, our data is young, and our techniques are still evolving. The true leviathans, the silent massive kings of the outer darkness, are likely still hiding, waiting to be discovered. So, what is the biggest planet in the universe? For now, the title is split. For biggest by sheer size, the puffy low-density worlds like WASP-17b hold the crown. For biggest by mass, the dense super-Jupiters and young massive objects like ROX 42b push the very definition of a planet, nearing the threshold of a star. And for the biggest known structure, the debated rings of J14407b show us that planets can build on scales we never imagined. The final answer depends on the yardstick you choose, radius, mass, or sheer spectacle. But one truth stands above all. These giants are a testament to the universe's ability to create objects of both breathtaking beauty and terrifying power. They are humbling reminders of the forces at play in the cosmos. If that sense of awe and terror hits you too, subscribe and come back for more explorations of the extreme. Because the next shadow we see crossing a distant star could rewrite everything we think we know about what a planet can be.